Let's start with what everybody thinks they already know. Gravity. Easy, right? You drop your keys, they fall. You jump, you come back down. You step on a scale, it gives you a number, and you say, that's my weight. End of story. Earth pulls, things go down, done. We learn this so early that it feels almost silly to question it, like questioning why water is wet. And that's exactly why it's dangerous, because the ideas we learn first, the ones that feel obvious, are usually the ones we stop examining. We wrap them up with a word, gravity, tie a nice bow on it, and put it on a shelf in our minds labeled understood, and then we never look at it again. But let me ask you something simple. When you say the earth pulls me down, what picture pops into your head? Be honest. Is it like an invisible hand grabbing you, or a rope tied around your waist pulling you toward the center of the earth? Maybe something like a magnet? We all carry around some picture like that, even if we've never said it out loud. Now here's the funny thing. That picture doesn't come from observation, it comes from habit. Because if you actually slow down and pay attention to what you experience, gravity already starts acting strangely. For example, stand still for a moment. Just stand there. What do you feel? You say, I feel gravity. But do you? Or do you feel the floor pressing up against your feet? If the floor suddenly vanished, don't worry, just imagine it wouldn't pull you down faster. The push would be gone. That's interesting already, isn't it? We say gravity pulls us down, but in everyday life, all our sensations come from things pushing on us. Chairs push, floors push, scales push. Even when you're lying in bed, the mattress is pushing back. Gravity, whatever it is, never taps you on the shoulder and says, hey, I'm pulling you now. It works quietly, indirectly, almost shyly, and yet we talk about it with great confidence. Things fall because of gravity. Well, yes, but that's not an explanation. That's just restating the observation with a fancy label. It's like saying opium makes you sleepy because it has a dormitive power. That sounds impressive until you realize you haven't learned anything new. The truth is, gravity feels simple because we've lived with it our whole lives. We're born into it. We grow up inside it. We don't remember a time without it. So we confuse familiarity with understanding. But nature doesn't care how familiar something feels. If you look closely, she's always doing something a little stranger than your first idea. And that's the fun part. Because once you admit, even just a little bit, that the obvious picture might be wrong, a crack opens. And through that crack, much more interesting questions sneak in. Questions like, what does it really mean to fall? Why does standing still feel like effort? And why do things move the way they do when nobody seems to be pulling them at all? So before we explain anything, let's do something much more important. Let's agree to be suspicious of the obvious. Because gravity, as ordinary as it seems, is already quietly telling us that our everyday picture might not be the whole story. And if that picture is wrong, then what's actually going on? Now let's take that crack we made and widen it just a little. Because once you start paying attention to what you actually feel, gravity starts behaving in a very odd way. Stand up again. Don't do anything dramatic. Just stand there like you always do. What sensations are coming from your body? Pressure in your feet, maybe a bit in your legs. If you're leaning, pressure in your back or shoulders. All of it comes from contact, from things touching you and pushing on you. Now here's the curious part. That thing everyone talks about, gravity pulling you downward, you never feel it. Not once, not ever. There is no sensation of being tugged toward the center of the earth, no downward yank, no internal feeling of being dragged. All the information your body gets comes from surfaces pushing back at you. If you're sitting in a chair, the chair pushes up. If you're lying on the floor pushes up. If you're standing on a scale, the scale pushes up and complains about it by showing a number. That number isn't measuring how hard Earth pulls you. It's measuring how hard you are pushing down on the scale and how hard the scale must push back to keep you from moving. That's already a little unsettling, isn't it? We're used to saying, I feel heavy because gravity is pulling me down. But the feeling of heaviness comes from being squeezed, compressed, supported, from resistance, from being prevented from moving. When you jump off a diving board, that heaviness disappears instantly. You don't feel as stronger. Pulled downward, you feel lighter. Sometimes you even feel weightless for a moment. But gravity didn't turn off. If it did, you'd float away. So why does the feeling vanish? Because the push vanished. Here's a simple test you can imagine. Suppose you're in an elevator. The cable snaps again. Just imagine no lawsuits here. The elevator and everything inside it start falling together. What do you feel? Not an increased pull downward. You feel nothing. Your stomach might flutter, but your body stops feeling heavy. The floor isn't pushing on your feet anymore. You and the elevator are moving together. And yet gravity is still doing whatever it was doing before. That should make you pause. Because it means the sensation we casually call gravity isn't really gravity at all. It's what happens when gravity is interrupted, when something like the floor gets in the way and says, no, you're not going to move like that. This turns our everyday picture upside down. We think gravity causes weight, but weight only appears when motion is blocked. You feel heavy not because you're being pulled, but because you're being held back. Imagine holding a book in your hand. Your arm gets tired. You say, the book is heavy, but what's actually happening? The book wants to move. Your hand prevents it, your muscles strain. The effort comes from stopping motion, not from motion itself. That same idea applies to you standing on Earth. So the next time you say, I feel gravity, try correcting yourself just for fun. Say, I feel the floor, because that's what's really happening. And once you see that, a strange new question pops up all on its own. If gravity doesn't feel like a pull, and falling doesn't feel like anything at all, then which one is the natural state, and which one needs explaining? That question is where things start getting really interesting. Now let's take everything we've said so far and point it at the sky, because that's where the trouble really begins. Look at the moon. It's been up there a long time. Billions of years, hanging around Earth like a loyal companion, and we're told it stays there because gravity pulls it in. Fine, sounds reasonable. But then comes the awkward question, if gravity is pulling the moon toward Earth, why hasn't it landed yet? I mean, if I drop my keys, they don't circle my hand politely for a few billion years. They fall, they hit the floor, end of story. So what kind of pull pulls something forever without ever pulling it in? The usual answer is the moon is moving sideways. Ah, now we're getting somewhere. Imagine throwing a rock. If you throw it gently, it lands nearby. Throw it harder, it goes farther. Now imagine throwing it so hard that as it falls, the earth curves away beneath it. It keeps falling, but keeps missing. That rock never lands. It goes all the way around. That's the moon. The moon isn't staying up. It's not balanced. It's not hovering. It's falling. Falling all the time, just like your keys. The only difference is that it's moving sideways fast enough to keep missing the earth. That sentence alone should make you uncomfortable with the old picture, because falling is no longer something special. It's the default behavior. The moon isn't fighting gravity. It's obeying it completely. It's doing exactly what falling things do, just on a much grander scale. Now think about how strange that is. The moon has been falling toward Earth for billions of years and has never once gotten closer. That's not how ropes work. That's not how magnets work. That's not how any ordinary pulling force behaves. If I tied a rope to the moon and pulled, it would come in. Slowly, maybe, but it would come in. Gravity doesn't behave like that. It creates motion that curves instead of collapsing. And here's another odd detail. The moon doesn't feel anything while it's doing this. No strain, no tug, no resistance. It's just moving. Smoothly, calmly, quietly, like it's not being forced at all. In fact, if you were standing on the moon or floating with it, you wouldn't feel gravity from Earth pulling you sideways. You'd feel nothing. Just like the elevator falling earlier, just like astronauts in orbit. So now we're in a strange position. We have a force that makes things curve instead of crash, causes constant falling without impact, produces motion without sensation. That should already tell you something important. Whatever gravity is, it's not behaving like the forces we're used to in daily life. And there's one more twist. The moon isn't special. Satellites do the same thing. Space stations do the same thing. Even astronauts floating peacefully inside a capsule are doing the same thing, falling around Earth. So orbit isn't an exception to gravity, it's gravity on full display, which raises a deeper question. If falling is so natural, so effortless, why do we think of gravity as something that acts on objects? Why do we imagine it as a pull at all? Maybe we've been focusing on the wrong thing. Maybe the real mystery isn't why things fall, but why they ever don't. At this point, something sneaky has been happening, and it's worth slowing down to notice it. Every time we run into a question, why did it fall? Why does the moon curve? Why do I feel heavy? There's a very tempting move we make. We say one word and feel satisfied. Gravity. That word has a wonderful calming effect. It makes us feel like the problem has been handled, case closed, like saying because nature, or that's just how it is. But if you're being honest with yourself, nothing has really been explained. You've just given the mystery a name. This happens all the time, not just with gravity. Suppose you ask why a sleeping pill makes you drowsy, and I tell you, because it has a sleep-inducing property. Well, thank you very much. Now I know exactly as much as I did before. I've replaced my question with a label. Gravity often works the same way. You drop your keys, they hit the floor. Why? Because of gravity. But what does that actually mean? Did anything happen in that explanation, or did we just nod politely and move on? The danger is that once something has a name, we stop poking it. The name feels like understanding. And gravity has had a name for a very long time. So long, in fact, that most of us never question whether the name is hiding confusion instead of clearing it up. Here's a simple test you can try. The next time someone says, "It happens because of gravity," ask gently, not obnoxiously, "Okay, but what does gravity do?" Don't ask for equations. Don't ask for big words. Just ask what actually happens physically. You'll notice something interesting. People often start repeating the same sentence in different forms. Well, mass attracts mass, or objects pull each other, or that's just the force of gravity. But that's the same idea wearing different hats, and here's the uncomfortable part. For a very long time, even scientists were in that same position. They could describe gravity perfectly, predict it, calculate it, use it to explain tides, orbits, falling apples, and planetary motion. But when it came to explaining how it worked, what was actually going on, they had to shrug. And shrugging is okay, as long as you know you're doing it. The problem isn't ignorance. The problem is pretending we're not ignorant. When we say gravity pulls, we're sneaking in a picture from everyday life. Pulling is something ropes do, muscles do, hands do. But gravity doesn't look like any of those. There's no contact, no stretching, no visible connection. And as we've already seen, it doesn't even behave like a normal pull. It makes things fall forever without landing. It makes objects move without feeling anything. So when we say because of gravity, what we often mean is there is a pattern here, and we have a rule that describes it. That's valuable. That's real knowledge. But it's not the same as understanding the underlying mechanism. And here's the beautiful part. This isn't a failure of science. It's one of its strengths. Real science keeps track of what it knows and what it doesn't. It doesn't hide confusion behind vocabulary. It puts a little flag there and says something interesting lives here. Gravity is one of those places. So if the word itself isn't an explanation, and the pull picture keeps breaking down, then maybe the next step isn't to add more words. Maybe it's to change the picture entirely. Now, before anyone thinks I'm being unfair to gravity or to the people who worked it out, let's stop and give credit where it's due. Because one man, Isaac Newton, did something astonishing, truly astonishing. Newton figured out a rule, a simple rule, a rule so good that once you write it down, the motions of apples, moons, planets, tides, and comets all fall into line like well-trained soldiers. With this one idea, you can predict where Mars will be next year, when an eclipse will happen, and how fast a stone will hit the ground. It works beautifully. It works so well that we still use it today. That's not nothing. That's a triumph of human thought. But here's the part people often miss. Newton told us how gravity behaves, not what it is. That difference matters. Newton said that every object attracts every other object. The bigger the masses, the stronger the attraction. The farther apart they are, the weaker it gets. That's a description, a very precise one. You can plug in numbers and get answers that match reality to an incredible degree. But if you asked Newton the obvious next question, how does one object reach across empty space and affect another? He didn't pretend to know. In fact, he was quite uncomfortable with it. He called it action at a distance. And he openly admitted that the idea bothered him. How does the Earth know where the moon is? How does the moon know instantly if something changes on Earth? What's carrying the message? Is there a rope, a signal, a push? Newton had no picture for that. And instead of inventing a story, he did something very honest. He said, essentially, this is how it behaves. I don't know how it works. That honesty is important because what happened next over the centuries is that people quietly forgot this distinction. The equations worked so well that we began to talk as if the explanation had been completed. Mass attracts mass stopped sounding like a description and started sounding like a mechanism. But saying they attract is not explaining how they attract. Imagine if I told you two people fall in love because of romantic force. You could measure it, maybe predict it, write poetry about it, but you still wouldn't know what's actually going on inside their heads. You just have a rule that happens to work. Newton's gravity is like that. Powerful, predictive, incomplete. And there's another subtle clue hidden in his success. Newton's gravity works instantly. Change the position of the sun, and according to the theory, the Earth responds immediately. No delay. No travel time. Across millions of miles of empty space, the influence is just there. Even Newton thought that was strange. But again, because the math worked, people stopped worrying about it. They took the rule and ran with it. They used it to build bridges, aim cannons, navigate ships, and eventually launch spacecraft. And for all of that, Newton's picture is more than good enough. But if you're curious, truly curious, you start to notice that something is being swept under the rug. A perfect description paired with a missing explanation. And nature has a funny habit. When two very different things line up too perfectly, when a rule works too smoothly, it's often a hint that there's a deeper idea hiding underneath. Newton gave us the behavior of gravity, but the secret he left behind, the one he himself worried about, is that behavior isn't the same as understanding. And that secret is what finally led someone else to ask a very dangerous question: what if gravity isn't a force at all? Now here's a detail about gravity that sounds boring at first, but turns out to be one of the most shocking clues we've ever found. It's so familiar that we barely notice how strange it really is. Drop two things, a hammer and a feather. In ordinary air, the hammer hits first. Everyone nods. No mystery. But take the air away, put them in a vacuum, and something very odd happens. They fall together, exactly together. They hit the ground at the same time. Now, stop and think about that for a moment. The hammer is heavy, the feather is light. Common sense says the heavier thing should be pulled harder. And according to Newton's rule, it is pulled harder, much harder. The earth pulls on the hammer more than it pulls on the feather. So why doesn't the hammer race ahead? Because the hammer also resists motion more. It's harder to get moving. And somehow, miraculously, these two effects cancel out perfectly. Not approximately, not most of the time. Perfectly. Bricks, feathers, cannonballs, grains of sand, everything. That should make you suspicious. Newton's theory needs two separate ideas to make this work. One is gravitational mass, how strongly something responds to gravity. The other is inertial mass, how much it resists being accelerated. There is no obvious reason those two things should be related at all. One is about attraction, the other is about stubbornness. And yet, in every experiment ever done, they are exactly proportional, always, everywhere. That's not just convenient, that's eerie. It's as if nature is whispering these two things you think are different aren't. Newton noticed this, of course. He had to. His equations depended on it, but he didn't know what to make of it. He treated it as a coincidence, an incredibly reliable coincidence, and moved on. Most people did the same. But imagine you're a curious person who doesn't like coincidences. Imagine you're bothered by the idea that two unrelated properties of matter just happen to match perfectly for no deeper reason. You might start to wonder whether you've divided the world up incorrectly. Maybe gravitational mass and inertial mass aren't two things. Maybe they're the same thing, wearing different disguises. Here's another way to look at it. When something falls, it doesn't matter what it's made of. Wood, iron, water, dust, it all moves the same way. Gravity doesn't seem to care about composition, texture, shape, or history. It treats everything equally. That's very unusual for a force. Most forces discriminate. Magnets care about materials. Friction cares about surfaces. Air resistance cares about shape. Gravity doesn't care about any of that. It treats everything with the same indifference. So maybe gravity isn't acting on objects in the way we imagine. Maybe objects aren't responding to a pull differently because of their mass. Maybe they're all doing the same thing for a deeper reason. And notice something else. When you fall, really fall, you don't feel heavier. You feel lighter. Sometimes you feel nothing at all. Falling doesn't strain you, it doesn't press you, it doesn't resist you. Standing still does. So here's the uncomfortable thought. What if falling isn't being forced to move, but being allowed to move? What if the hammer and the feather fall together not because gravity pulls them equally well, but because neither one is being forced at all? That idea sounds crazy at first, but it explains the coincidence perfectly. It explains why mass doesn't matter. It explains why falling feels effortless. And once you let that idea in, even just a crack, you're ready for a thought experiment so simple and so devastating that it will quietly rearrange your entire picture of gravity. All right, now comes one of my favorite tricks, not because it's clever, but because it's so unfairly simple. It sneaks up on you. You think you've got gravity figured out, and then this little thought experiment quietly pulls the rug out from under the whole picture. Imagine you're inside a small room. No windows, no clues, just you, the floor, and a few ordinary objects. You feel your usual weight. Your feet press into the floor. If you drop a ball, it falls straight down and hits the ground. Everything feels normal. Question, are you standing on Earth, or are you in a rocket, far out in empty space, accelerating upward? Take your time. There's no rush. Because here's the uncomfortable answer, you can't tell. Drop the ball in both situations, it falls the same way. Stand on a scale, it reads the same number. Toss the ball sideways, it curves the same way. Lean against the wall, it presses back with the same firmness. Every experiment you can do inside that room gives the same result. That should bother you, because if gravity is a force pulling you down, and acceleration is something entirely different, then why do they look exactly the same? Now imagine the opposite situation. You're in that same closed room, but suddenly the cable snaps or the rocket engines shut off. Everything inside starts falling together. You, the floor, the scale, the ball. What do you feel? Nothing. You float. The scale reads 0. The ball hangs beside you like it forgot how to fall. It feels exactly like drifting in deep space far from any planet. But here's the twist. Gravity didn't go away. If you were near Earth, gravity is still acting just as strongly as before. The only difference is that nothing is resisting it anymore. Everything is moving together. So now we've got a strange pairing. Standing on Earth feels the same as accelerating in space, and falling near Earth feels the same as floating far away. That's not a coincidence. That's a clue. It tells you that gravity and acceleration are not just similar, they might be the same thing, seen from different perspectives. The feeling you call weight isn't a sign of being pulled downward, it's a sign of being pushed upward, of being prevented from moving the way you otherwise would. Think about that for a moment. When you're standing still on the ground, something is constantly pushing you. The floor, the chair, the bed. They're all interfering with your motion. They're forcing you off whatever path you'd naturally take if nothing were in the way. When you fall, that interference disappears, and suddenly peace, weightlessness, effortlessness. So here's the quiet revolution hidden in this elevator. Gravity doesn't announce itself with a tug. It doesn't grab you by the ankles. It shows up only when something stops you from moving freely. That's a completely different way of thinking about it. And once you accept that, once you really let it sink in, the next idea almost suggests itself. Because if falling feels like freedom and standing feels like strain, then maybe falling isn't something that needs explaining at all. Maybe falling is the natural state. And if that's true, then what exactly is the ground doing to you right now? Now, this is the part where your intuition really starts to protest. Because everything you've been told since childhood is about to be flipped upside down. We're used to thinking that falling is something that happens to objects, something dramatic, something caused. You fall because something acts on you. Gravity does something, pushes you, pulls you, makes you move. But what if that's backwards? What if falling is what happens when nothing is acting on you? Think back to the elevator. The moment the cable snaps, again, just imagine you don't feel a stronger pull. You don't feel rushed downward. You feel relief. The pressure disappears. The floor stops pushing on your feet. Your body stops being squeezed. You're not being yanked anywhere. You're finally allowed to move the way you were trying to move all along. That's a very strange thing to admit. It means that falling doesn't require effort. It doesn't require force. It doesn't even feel like anything. Falling is quiet. Standing is noisy. Standing requires constant interference. Right now, as you're listening to this, you are not peacefully at rest. You're being shoved upward by the ground continuously. The floor is pushing on your feet on your legs on your bones. There's a whole chain of pushes happening just to keep you where you are. If that pushing stopped, even for a moment, you wouldn't suddenly be grabbed by gravity. You'd simply continue along the path you were already trying to follow. So here's the uncomfortable reversal. Standing still is forced. Falling is free. That sounds wrong because we've built our whole mental picture the other way around. We imagine space as passive and gravity as active. But all our experiences are hinting at the opposite. Motion, smooth, effortless motion is what happens when nothing interferes. What needs explaining is why objects ever stop doing that. This is exactly the same shift Galileo made with motion. People used to think things naturally come to rest, that motion requires a cause. But Galileo noticed something simple: remove friction and motion keeps going, forever. Motion doesn't need explanation, stopping does. The same logic applies here. When an apple falls, it isn't being forced into motion. The branch was forcing it not to move. When the branch breaks, the interference ends. The apple is free. When the moon orbits Earth, it isn't being dragged sideways by some invisible tether. It's moving freely, following the path available to it. Nothing is pushing it along that curve. There's no strain, no tension, no effort, just motion. And when you're standing on Earth, you're the one being interfered with. You are the odd case. You are the object being prevented from doing what everything else is quietly doing all the time. This is why astronauts feel weightless in orbit, even though gravity is still strong. Nothing is holding them back. Nothing is in the way. They are free. So now we've arrived at a very strange place. Gravity doesn't act like a force that makes things fall. Falling happens when forces disappear. Gravity shows up only when something resists motion. Which leads us to a question we've been carefully avoiding. If nothing is pulling objects, and falling requires no force, then what is gravity actually doing? To answer that, we're going to have to let go of the idea of gravity as a push or a pull altogether and replace it with something far stranger and far more beautiful. All right. If you've stayed with me this far, you've already done something brave. You've let go of a very comfortable picture, the idea that gravity is some invisible hand yanking things downward. And now we're standing in a slightly empty space, asking, if nothing is pulling, then what on earth or off earth is going on? Here's the key move, and it's subtle, so don't rush it. Suppose I tell you that an object moving freely, no pushes, no pulls, nothing touching it, will always follow the straightest possible path. That sounds reasonable. It's not a fancy idea, it's just what doing nothing looks like. If nothing interferes, things don't suddenly decide to curve or zigzag, they go straight. Now here's the twist. What if the straightest possible path isn't what you think it is? We're very used to thinking of space as a flat stage, like a giant invisible grid where things move around. Straight lines are straight everywhere. Up is up, down is down. Simple. But imagine living on the surface of the earth without ever knowing it was round. You walk straight ahead and never turn. Eventually, you come back to where you started. Did you curve? From your point of view, no. You walk straight the whole time. It's the surface that was curved. That's the trick. What if space itself isn't flat in the way we casually imagine? What if mass, things like Earth, the sun, the moon, change the shape of the space around them? Not by pulling on objects, but by quietly reshaping the paths objects naturally follow. Then everything we've been talking about suddenly clicks. The apple isn't being pulled downward, it's following the straightest path available to it. Near Earth, that straight path just happens to point inward. The moon isn't being tugged sideways by an invisible cord. It's moving straight ahead through space that's curved around Earth. What looks like a circle to us is just the moon minding its own business in a bent environment. No pulling required. This idea feels strange because we're trying to picture it using instincts built for flat floors and straight hallways. But nature doesn't care about our instincts. She cares about consistency. And this picture explains a lot of things with surprising elegance. It explains why everything falls the same way. They're all following the same geometry. It explains why falling feels effortless. Nothing is acting on you. It explains why standing still feels heavy. Something is preventing you from following that natural path. And notice how gentle this explanation is. There's no mysterious force reaching across empty space, no instant signals, no invisible ropes, just objects moving freely and space quietly telling them which paths are available. Now, I want to be very honest here. Saying space is curved doesn't magically make everything obvious. It's not a picture you can easily draw with crayons. It's not something you can feel directly. In that sense, it replaces one mystery with another. But it's a better mystery, because instead of inventing a force that pulls without touching, we're saying something deeper. Maybe what we call gravity is just the shape of the arena we're moving in. Maybe objects don't need to be told how to move. Maybe they're already doing the simplest thing possible. And once you accept that idea, a lot of familiar phrases start to sound suspicious, like zero gravity, or escaping gravity, or even standing still, which brings us to the next puzzle. If gravity isn't pulling and free motion feels like floating, then why do astronauts feel weightless while you and I feel so heavy right now? That's where the story takes its next turn. Now, this is where a lot of people feel cheated. You see pictures of astronauts drifting around a space station, smiling, doing little flips, and someone says they're in zero gravity, and everyone nods because that sounds reasonable. But it's wrong, very wrong. Here's the surprising fact. The gravitational pull-up where astronauts orbit Earth is almost as strong as it is down here. Not half, not a tiny bit. Almost the same. If gravity were something you could turn into a number, it would still be working at about 90% strength. So why are they floating? If gravity were a pulling force, this would make no sense at all. Strong pull should mean strong weight, yet they feel weightless, completely free, like nothing is acting on them. And that's exactly the point. The astronauts aren't floating because gravity is gone. They're floating because nothing is stopping them. The space station is falling. The astronauts are falling. The tools, the air, the crumbs from lunch, everything is falling together. They're all following the same natural path. No one thing is being held back more than another. Think back to the elevator. When everything falls together, weight disappears. The scale reads 0. The pressure vanishes. Not because gravity switched off, but because there's nothing pushing. Weight comes from resistance. On Earth, the ground resists your motion. It blocks your natural path. It pushes up on you. That push is what you feel. In orbit, there is no ground in the way, no floor pushing back, so there's no weight. The astronauts are not escaping gravity. They are doing the purest version of what gravity allows. Free motion. Here's another way to picture it. Imagine you're running and someone suddenly grabs your shirt. You feel the tug. That's force. Now imagine no one grabs you. You keep moving, smoothly, effortlessly, no sensation at all. That's orbit. The space station isn't being held up. It's not balanced. It's not hovering. It's constantly falling toward Earth just like the moon. But it's moving sideways fast enough that the Earth curves away beneath it. It keeps missing. So inside the station, everything feels calm. No up, no down, no heaviness, just motion. And this is the part that really messes with our intuition. The astronaut's experience floating freely is actually closer to the natural state of motion than yours is right now. They're doing what objects do when nothing interferes. You, on the other hand, are being interfered with constantly. The floor is pushing on you. The chair is pushing on you. Even your bed pushes on you while you sleep. That push is what makes you feel heavy. Not gravity reaching down, but matter pushing up. Once you see this, phrases like zero gravity start to sound suspicious. There's no such thing in orbit. Gravity is very much there. What's missing is resistance. And that brings us to a quiet realization. If floating is what happens when nothing gets in the way, and weight is what happens when motion is blocked, then gravity itself isn't something you feel. It's something you stop feeling when you're allowed to move freely. Leads us to the final shift in imagination. If gravity isn't pulling and space itself is shaping motion, then maybe the picture we need isn't about forces at all. Maybe it's about paths.